So on the balances or mass measuring scales, we have three devices to take a look at: triple beam balance, four beam balance, as well as the electronic balance. Right. So we'll first go to triple beam balance and we'll see how it works. Right. So the basic principle behind the triple beam balance is the moments principle. It works with moments principle. That is the basic principle of the triple beam balance. So how does it work with this moment principle? So this whole part, it works as a single rod. This whole part works as a single rod, which is being pivoted from this point. It works as a single rod, which is being pivoted at this point. So it's the pivoting point. So when you put a weight on this scale, it is going to produce a moment towards the anti-clockwise direction, right? So that moment can be balanced using these movable masses. So you have here three beams. That's why we call this the triple beam balance. We have three beams. So these three beams, on these three beams, you have three movable masses. So once you move these masses, they are capable of producing a moment. So when the moment produced by the mass that we keep on the scale pan is equal to the moment produced by these movable masses, is where it balances. So at that point it gets balanced. So at that point we can see the balancing reference here is at the 0 mark. You can see there's a 0 mark here. So that balancing reference comes to the 0 mark at that particular instance, where the clockwise moments are equal to the anti-clockwise moments. So in order to make them equal, you will have to move these movable masses. So when you move these movable masses, from the positions of the masses, you can get the readings as well. So the principle behind this triple beam balance is the principle of moments, right? Okay, so let's see what else we have in this. Right. So let's try to identify the components. This is the scale pan where we keep the mass that we want to measure on, and the triple beams, balancing reference. So when this comes to the 0 position, it can move up and down, right? When you keep a mass on this whole thing will go up like this. Now when you move the movable masses and when the clockwise moment is high, the whole thing will go down as well. So this part of this beams can go up and down. So when it comes to this point, right now what you can see is it's balanced, right? So when it comes to the 0, when the line here, the white line here is aligned with the 0 point, 0 mark, we say it's balanced. So that is why we call this the balancing reference, right? And there's a small knob here you can see, which you can rotate. So when you rotate this small knob, it has a weight, that's a small weight. So when you rotate this knob, that it can go frontwards or backwards. Once you rotate it, you can move it frontwards or backwards. So when you rotate it frontwards or backwards, because of its weight, there is a certain moment. You can change that moment because the distance from the pivoted point to that mass is going to change once you rotate it, right? So it can change a small moment that it gives. So why do we need to have that small moment? We call it the fine adjustment. Why? Because when no mass is kept on the scale pan and when the movable masses are all at 0, then this should come to the balancing reference. It should come to 0 in the balancing reference. But sometimes when you use this device, it might come to a certain position where it's not getting balanced as it is required to. So what we can do is we can rotate this fine adjustment, and before getting any reading, before moving movable masses, before putting any mass on it, we can make sure that it has come to the zero in the balancing reference. So we are using it to make sure that it comes to the balancing reference before we start using the device. Right. Okay, so let's see how do we get a reading here. So in this you can see an enlarged image of the same. So we have 3 beams. These are 3 beams. Okay, let's try to read the beams. So in this smallest beam, in this the first beam, you can see it says 10 grams, and you can see here between this point to this point, you can see it's 9 grams and 10 grams, and it's been divided into 10 divisions. So there's 1 gram here, and it's being divided into 10 divisions. So 1 divided by 10, so we can see that it's a 0.1 gram least count. It's a 0.1 gram least count, because this scale, this beam has the lowest values, and out of the lowest values, once you divide, you can see there are 10 small divisions between 9 to 10, so it's 0.1 gram. So the least count here is 0.1 grams. You can also see that the least count, no, in this one they have not stated, as I see they have not stated the least count. Right, so this is how we check the device and get what the least count is. So here the least count is 0.1 grams. You have to memorize that in triple beam balance. The least count is 0.1 grams. Right, and if you go to the second one, you can see there is 500 grams. 0, 100, 200, 300, 400 and 500 you can see. And also in the one above you can see 100 grams. So when you move this small mass to this point, and this larger mass to this point, and this small mass to this point, you can get the maximum reading of this device. That maximum reading will be 100 grams on the top, 500 grams in the middle, and 10 grams at the bottom. So that will add up to 610 grams. So using these 3 beams, you can get 610 grams of a maximum reading. And also you can see a small difference between these beams. So the beam, the lowest beam, now if you take this beam is different from the other 2. You can move this small mass, the movable mass, to any point that you like in this. But here you can see there are a few cuts. They are made cuts. Right, you can see there are small cuts here. So you can move these masses only to these positions. They have marked positions. Small cuts are there, so when you slide it along, it is getting fixed to that small gaps that they have made on this. So you can't move it continuously, they move discretely. You can't move those 2 continuously. So there is a difference between these 3 beams. 2 are like 2 work discretely, and the other one works continuously, as you can see. So we found out that it's 610 grams that we can measure using this. But the thing is, when you take a look at this, you can see that they have said the capacity is 610 grams slash 2610 grams. What is that? 2610 grams. They say Also, we can measure 2610 grams. Yes. So this device comes with an extendable range. Right? There is an option. Now this comes with an option of an extendable range. You can extend the range here. So the range extender here is actually this device. So with this you get a few set of weights. A set of weights. So this set of weights you can hang from this point. You can hang this set of weights from this point. So each of these weights, say an example, will weigh of 500 grams maybe. Or you might also have directly 2000 gram weight. Or you might have 500 grams weight. So let's say it's a 500 gram weight. So when you hang it here, when you hang this 500 gram mass here, you can say it reaches directly 500 grams. So with this 500 grams and with this 610 grams, it is 1110 grams now. So if you put another 500 grams, then it's 1000 grams. Likewise, you can extend the range here. It's a range extender, right? It's a range extender. So they say that you can measure 2610 means they're going to give 2000 grams extra here. They're going to give, it's not the mass actually. It's not the mass of these weights. It's not 200 grams. Not that one will weigh, all of these will weigh 2000 grams. No. But they will create a moment which is equal to 2000 grams. So these are range extenders. So in this device, we have a range extender. Right. So here's a small note that you can refer to this note as well. So in this slide also you can see the note. You can make a note, you can write it down. And the range of this, the least count is 0.1 grams as we just found out, and range might change depending on the device. Our second device is the 4-beam balance. 4-beam balance. So in this, the principle is the same as previous that we discussed, right? So this part works as a rod which is being pivoted at this point. So this also works with the principle of moments. So the difference is there are small differences in this. We have 4 beams here. So there are 4 movable masses. 3 move discretely from point to point. There are positions, right? So only these three movable masses can be positioned to these cuts that they have marked. And we have this small mass which moves continuously on it. So anyway, we have 4 beams here. And also the other difference in this device is that we can hang a mass, right? So there is a scale pan they have given. You can see scale pan is also hung, right? They have given a scale pan which is also hung. And also if you want to hang something, you can remove this scale pan from here and you can hang whatever the mass that you want to weigh. So you can hang it as well. So what is the importance? They might ask, what is the importance of hanging a mass here? What is the importance of hanging? Why can we not keep it on the scale pan? Why do we need to have to hang it? You know, there are some experiments in which, like finding the relative density experiment, right? We have some experiments like finding relative density. You'll have to weigh a mass inside a liquid or inside the water. You have to weigh that. So to get the apparent weight, in order to find the apparent weight, you know what is the apparent weight is mg minus u, the weight minus the upthrust. If you want to get weight minus upthrust, you will have to hang it and you have to immerse it in a liquid. So with this balance, you can do that, right? But it's difficult to do that in the other one, right? In the other one, in the sense, which is the triple beam balance. Not that it is totally impossible in triple beam balance. In triple beam balance also there is a way to do that, right? There is a way to do that. You can keep that the vessel on the balance, then you can immerse the object from like you are holding it, then also you can get the same thing, but it's a bit difficult. But in this one it's easy, right? Because this is made anyway to hang a mass and weight, right? So this one also has the fine adjustment, balancing reference, the beams, everything is the same, right? So let's see what is the least count that we can obtain from this device. So you can see, I'll zoom this in. Let's take a good look at these 4 beams. So this beam is having 200 grams. So where we get is where we get 200 grams. And this beam has 100 grams on it. This beam has 10 grams. And this beam has 1 gram. So altogether, you can say it's 311 grams. And we don't see that there is a range extender here. We can't see something like that here. So there can be devices with range extenders, but in this device you can't see a range extender. So here the maximum value that you can measure is 311 grams. And let's check what is the least count. So in order to get the least count, you are getting the one with the minimum values, which is this one. Here you can see it goes from 0.9 grams to 1 gram. 0.9 to 1. Between 0.9 to 1 you have 0.1 gram, and that 0.1 gram is being divided into 10 divisions, you can see. So the least count of this device will be 0.01 grams. This is the least count of this device. So this is 1/10 accurate, or you can say not 1/10, 10 times accurate than this the previous device, the triple beam balance. So they have added one beam in order to make it more sensitive, we can say something like that, right? So this is how the triple beam balance works. So the principle is the same. It's the same previous principle of moments, right? So the range might change from device to device, and the least count remains as 0.01, right? So here's a note that you can add to your notes. The next one is the electronic balance. Electronic balance. So this is going to measure a mass using the electronic sensing methods, using electronic sensors, and also it has an electronic digital display which directly gives you the reading. So there are a few buttons on this. So there's a button, the fine adjustment button, the 0 button, we call it the 0 button, right? So a 0 adjustment button, when you press it, the readings become 0. So when there is nothing on the scale fan, you can press that button. So if there's a registered value, you can make it 0. So before getting any reading, just like we rotate the fine adjustment, we have to press this 0 adjustment button, so the reading comes to 0. Then you can keep your mass on it, then you can measure it. So this is like a very convenient and easy device to work with, right? No hassle, it's very easy to work with. So there are different devices, I mean with different accuracies, electronic balances. We cannot exactly say that this is the exact accuracy of the electronic balance, because that might change, right? With technology in future also this might change. So this is we can say this as one of the newest types of mass measuring devices. So generally it will go from 0.01 grams to 0.001 grams, like 1 milligram, or maybe 0.1 milligrams also, right? So there are like more accurate devices now, even though if we don't have that in our school labs. So we can't say it has a particular fixed least count, but we can say it might change from device to device. But one thing is for sure, that we cannot measure heavier masses using this device, because it's a very sensitive device. You can't put a huge load on this. And you can see in the electronic balance, there's something like a cage. There's a cage, you can see, like a glass cage, or maybe a plastic cage. You can see in all of these that there's a cage. Yes, why? Because this electronic balance is very sensitive. So since this is very sensitive, even for small pressure in the wind can make a reading here. A very small pressure change in the wind also might be able to affect the reading. So we don't need that variation when you're trying to measure something. So what we do is that we cover the scale pan with this cage, with this cover, so that the effects on wind and all is going to be negligible. Right, so this is what we have. We are going to learn about electronic balance. So let's do a small comparison of least counts of these three devices. Triple beam balance, the least count is 0.1 grams. Full beam balance, 0.01 grams. Electronic balance, this might go from 0.01 grams to 0.001 grams, or maybe even more accurate than that, right? So this is the summary of it. So the ranges also might change from device to device. Electronic balance is not being used to put measure heavier masses.